In this video, we're going to look how E cell, delta G, and K are all related to each other. Just as a reminder what these terms mean, E cell is the electronic potential of a battery, delta G gives free energy, and K is the equilibrium constant. So for spontaneous reaction, we can actually talk about all three of these in terms of a spontaneous reaction. So spontaneous reactions have a negative Gibbs, a positive E cell, and a K greater than 1. So a spontaneous reaction has all three of these. Any one of these means you have a spontaneous reaction. Therefore, if delta G is negative, E has to be positive and K has to be 1. And we can actually interconvert between all three of these different variables. And the first equation that we're going to look at is how to convert between delta G and E cell. And we have this equation. Delta G equals negative N, which is the number of electrons in a reaction, F, the Faraday's constant, so just a constant, and E cell all multiplied together, and that'll give you a delta N. And if we take a look at this equation, you see if E cell is positive, which means spontaneous, then everything here will equal to be a negative. Negative times a positive number, which is N, times a positive number, which is F, times a positive number, which is E, is all negative. Therefore, if E cell is positive, delta G is negative. The other equation we have is delta G equals minus T ln K. R is the gas constant and T is temperature. So this is how you switch between an equilibrium constant and Gibbs free energy. And we also have going between E cell and K. All we can do here is we're just combining the two equations we just learned. So we know we have two reactions or two equations here for delta G. So if we set those equal to each other, we have minus NF E cell equals minus RT ln of K. And we can just rearrange this. So all I'm doing is I'm rearranging the equation here to say E cell equals RT divided by NF ln K, which is the equation on the diagram. Remember, R is gas constant, T temperature, N number of electrons, and F is the Faraday's constant. Now, if we're at 298, we can just already figure out what RT is, so that's 0.0592 if we divide it by F, that is. So RT and F at 298, that will be 0.0592, so all we need to worry about is N and K to find out E cell. Now, in this whole chapter, we've been talking about E cell and spontaneous reactions under standard conditions. That is, conditions chemists all agree on. You know, you have 1 molar of an aqueous solution or 1 atmosphere of gas. In the real world, though, most of the time you are not under those conditions. And so we need to be able to relate our measurements under standard conditions to those in real world conditions. And that's what these equations are showing. So the knot here, or the circle, is saying the Gibbs free energy at standard condition, or the E cell at standard condition. And so to switch between these for free energy, it will just be delta G equals delta G naught plus RT ln of Q. Remember, Q is related to K. It's your equilibrium constant at any point that's not equilibrium, or your reaction quotient is what Q actually stands for. And you also have minus NF E cell equals minus NF E naught cell plus RT ln of Q. What I'm doing here is I'm just rearranging equations. We don't need to know how we did that, just this is the rearranged equation. And again, I'm going to take RTF, get one value, and we get E cell under non-standard conditions equals our cell potential at standard conditions minus 0.0592 divided by number of electrons multiplied by our log Q, our reaction quotient. This is called the Nernst equation, and it allows us to calculate the E cell of a battery. Now, one type of battery that we haven't touched on yet are called concentration cells. So every battery we've talked about up to this point has been made of a different anode and a cathode. However, that doesn't have to be the only type of battery. You can use a battery in which your cathode and anode are the same material, but they're at different concentrations. And if they're at different concentrations, you can still get electrons to flow. That is what's called a concentration cell, and we can calculate the cell potential using the Nernst equation to determine which way electrons are going to flow. And generally, electrons flow from the less concentrated solution to the more concentrated solution. So less concentrated to more concentration is how our electrons are going to flow in our concentration cell. That's it for this video. In the next video, we're going to look at more batteries, so I will see you then.